Okay, so the next continuing chapter 4, homework problems, 67, 69, 71, 73, 75, 77, and 79. Now, these are based on the trends in the periodic table and the periodic properties. Okay, so we are going to look at the trends. Now, first of all, look at this trend. So right here you see is the group numbers. And you see, let me move this a little bit away, right here. All right, so you see here that you have the basic trends is the group number relates to the valence electrons. So hydrogen, lithium, sodium, potassium, all of them are ending in 1s1, 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 and 1s, in the s1, sorry. Depending upon what energy level they are in, this number corresponds to that. So it's first energy level, second energy level, third energy level, and fourth energy level. So, but all of them are ending in the s orbital, and there's only one electron in them. So the valence electron is 1. That is why these elements get placed in group number 1. And that is 1a. Group 2a. Group 2a has 2 valence electrons in the last shell, and those electrons are present in the s orbitals. And group number obviously is 2a because there are 2 valence electrons. So beryllium, 2 valence electrons. Valence electrons are the last electrons. Okay, so magnesium, 2 valence electrons. Calcium, 2 valence electrons. Depending upon what energy level they are in, you will have 2s2, 3s2, and 4s2. So now group 3a will obviously have 3 valence electrons. So the valence electron is the total number of electrons that are in the last shell. So the shell number is always the determining factor, and it's the highest shell number. So this is 2s2, 2p1, 3 electrons. 2s2, 2p1, 3 electrons. 2s2, 2p1, 3 electrons. Okay, so S and P combined together make it a 3. But second energy level applies to boron, third energy level applies to aluminum, and fourth energy level applies to gallium. Same is the case. We have now 4. 4a, 4 valence electrons, which are present in 2s2 and 2p2. Those are present in s2 and p2, right? s2 and p2, s2 and p2. But these are the energy level. 2s and 2p, 3s and 3p, 4s and 4p are the energy levels. So these are also called the rows in the periodic table. Nitrogen, phosphorus, and acetylene belong to 5a. 5a has 5 valence electrons. Where are they? s2 and p3. So second energy level is 2s2, 2p3. Third energy level is 3s2, 3p3. Fourth energy level is 4s2 and 4p3. So these, when added together, make 5, and that is 5a. Same is the case 6a. 2 plus 4 is 6a. 2 plus 4 is 6. 2 plus 4 is 6. So this 6 A valence electrons are 6, and they are present in, S and P. And depending upon what the energy level is, you will have 2s, 2p, 3s, 3p, and 4s, 4p filling. Next comes the 7a. 7a has 7 valence electrons in the last shell. So where are they? s2, p5, s2, p5, s2, p5. So all of them, 5 plus 2 makes 7. 7a, 7 valence electrons. Okay, so these valence electrons, if they belong to fluorine, it's in the second energy level. For chlorine, third energy level. Bromine, fourth energy levels. Okay, now the group number, yes, corresponds to the valence electrons, but the max out for us is 8. So except for helium. Helium is small, so it's 4s2. But look at neon, argon, and krypton. So 2 plus 6 is 8. 2 plus 6 is 8. 2 plus 6 is 8. Okay, so that is now whatever the energy level is, you will have that. So you get an idea now. Okay, so that is the valence electrons and the configuration. Now let's look at these valence electrons. Now, instead of writing those valence electrons, you can just show them as like dots. You will be doing this for the lowest structures anyways. So hydrogen has only one valence electron, one dot, lithium, one dot, sodium, one dot, potassium, one dot. All of them have only one valence electrons in their last shell. So it's 1A, one dot, 2A, two dots, 3A, 3 dots, 4A, 4 dots, 5A, 5 dots, 6A, 6 dots, 7A, 7 dots, and 8A, 8 dots, okay? So basically, you are just showing the valence electrons. Next is drawing the Lewis symbols based on those structures. Now let's look at the trends in the periodic table. Okay, so one of the trends is, and it's a little bit, it's contradictory. As you increase the atomic number, you should ideally expect the atom's size to increase. But the size decreases as you go from left to right in the periodic table. And the reason for that is in the end, these energy levels are just electron clouds. So these electron clouds, they spread out. When they are further away from the nucleus, they are spread out. But if they are very close to the nucleus, they are more compact. So that's one thing. Second thing is that the nucleus, the more the protons are in the nucleus, the size of the nucleus increases and the nuclear pull increases. The power to attract the electrons increase. Okay, so now there's another thing, that these electrons are actually present as waves and actually present as particles in the orbital. So you're going to learn about this more in other courses, but just keep this in mind that hydrogen, obviously 1 electron small, helium 1 electron small, but lithium and beryllium are smaller in size, even though they contain only 3 and 4 protons, than boron, carbon, nitrogen, oxygen, fluorine, neon. So these guys, so the size is decreasing because the nuclear pull also intensifies as you go from left to right in the periodic table. Like these guys, as more and more electrons are added, more and more protons are added, these protons, they pull the electron clouds towards itself, and then the electron cloud gets condensed or squished. So that's the reason why the atomic size decreases when you go from left to right. So by the size, we are actually meaning the radius. Okay, now as you go from top down, as you're going from top down, the energy levels are increasing. So the electrons are spreading out more. So that's why as you go top down in the same column, the size of the atoms increases. But when you go from left to right, then to some extent, the size decreases. Okay, now next is the other one is the ionization energy. Okay, ionization energy is the energy to remove the electrons, the energy to remove the electrons, okay, to create a positively charged, cation. So it's very difficult to remove the electrons of these, especially all the atoms that are present on this side. The ionization energy is more, means you need to provide more heat, more light, or more energy from your side to remove the electrons. It's not easy. So that's why the energy increases, or the energy is high. When you go top down, the energy decreases. And the reason for that is as you go top down, you are increasing the energy levels. And as these energy levels increase, what happens? As the energy levels increase, the nuclear pull decreases. Every shell that comes in between the other shell, so it blocks the look of the nucleus. The pull of the nucleus is blocked, and as a result, the nuclear pull, slows down or comes down. So the electron cloud spreads out. Okay, so top down, the energy decreases. Less energy is needed to remove the electron, but left to right, the energy level is increased. The ionization energy is increasing, or the ionization potential. Next is the metallic character. So we see that all the non-metals are here, all the metals are here. So all the metals are here, but the metallic character decreases. It is decreasing because obviously these are more on like more like these are all non-metals, and so they're obviously are not metallic. Okay, but as you go from top down, the metallic character increases. Okay, more and more metallic abilities. So these guys at the bottom will have more metallic abilities than the top ones. Okay, so we're going to study this when we compare. So let's start doing these problems. 67. Indicate the number of valence electrons in each of the following. So valence electron for aluminum. Let's do this one. So we will do 67, 69. One second. We're doing 67, 69, 71, 73, and then 75, 77, and 79. Okay, hold on. Okay, so now group 5A. So this 4.67 question is saying how many valence electrons are there. So remember, the group number corresponds to the valence electrons. So 5A means 5 valence electrons. Barium. Now, how many valence electrons are in barium? So let's say you don't remember. So here you look at the periodic table and look at that. Beryllium, magnesium, calcium, strontium, barium, radium. So how many valence electrons are going to be? Barium is in the sixth row. So six, and it is in the S block, and it is in the like S2 block. So 6s2. So let's do this here. Sorry. Okay, so barium is 6s2. So it has got 2 valence electrons. Okay, the rest of this you do it yourself. It's the same thing. You have to look at the periodic table to which elements belong to which group, and the group number represents the valence electrons, and then you just have to look at the periods. Okay, next is drawing the Lewis structure. Now sulfur belong in group 6A. Okay, so sulfur belongs to group 6A, and that means it has got 6 valence electrons. So that means you're going to make 6 dots. So here we have 1, 2, 3, 4, 5, 6. Okay. Nitrogen is in 5A. This has got 5 valence electrons, and that means 5 dots. Okay. Nitrogen. So let's look at this here once more time. Nitrogen, second energy level, and right here, nitrogen, third. Nitrogen is in the P3, okay, and that is the 2p3. So, 2p3. So nitrogen is 2p3, and then 2s2 is filled up. So these are the valence electrons. Valence electrons. And then that means nitrogen will have 5 bonds. 1, 2, 3, 4, 5. Okay. All right. Which one is a larger atom? So when you look at the trends in the periodic table, so when you look at the trends, and these trends are also given here in the handout. So here. So the trend. So we are looking at what trend is that? Larger, the size, So as you move from left to right in the periodic table, the size is the radial size comes down, decreases. Okay, but the size increases when you move from top to bottom. So size goes up when you move from top to bottom in the same column. So sodium and potassium are in the same energy level, but sodium is bigger than chlorine. Sodium is bigger than chlorine because it has a more spread out electron cloud. Rubidium or iodine. So look at this periodic table. So you have here iodine. Okay, and in no way iodine, and rubidium is, sorry, rubidium is right here, 5, energy level 5. So 5s1, and we are looking at, which one was that? Rubidium and iodine. Okay, iodine is right here. Iodine 53 and rubidium is 37. So same, in the same column. So iodine is smaller and rubidium is bigger. So remove that. So rubidium is definitely larger. Okay. Next is decreasing atomic side, aluminum, silicon, and magnesium. So look at that. So you have aluminum, you have silicon, and you have magnesium. Aluminum, silicon, and magnesium. So we see magnesium is smaller. Then comes aluminum, and then comes silicon. No, sorry, magnesium is bigger. So magnesium is bigger than aluminum, and aluminum is bigger than silicon. Okay, so rest, do it yourself. Next is the ionization energy. Which one has a more ionization energy? So bromine has more ionization energy. Okay, bromine is more ionization energy. More energy is needed because iodine is a big atom. So, it has got the spread of the electron cloud is more. Then the ionization energy is of which one? Fluorine, chlorine, bromine. So the ionization energy is the energy to split remove the electrons. So for the fluorine is the highest, then chlorine, then bromine. Okay, metallic character, which one? Bromine, germanium, calcium, and sorry, is it metallic character? So bromine, calcium. Okay, so bromine, calcium. Calcium is 20, and then bromine. The bromine. So yeah, so calcium, and then what was the other one? So here you have bromine is a non-metal, obviously, calcium, and germanium since like in between. So it's going to be calcium is more than germanium, and then more than bromine. Okay, so with that said, this finishes your homework, and I'm sure you're going to do the do-it-yourself problems so that you get good practice. All right. Thank you so much for watching, and bye-bye.